All right, today we're going to dive deep into the invisible force that connects pretty much everything, from a tiny spark to a massive bolt of lightning. We're talking about the electric field. Now, if you're prepping for exams like WAEC, JAMB or NECO, this is one of those topics you absolutely, positively have to know. And don't worry, we're going to break it down so it all makes perfect sense. So, have you really thought about it? What's the link between that little static shock you get from a doorknob and a huge, powerful lightning strike? I mean, they seem like they're worlds apart, right? Well, the answer is the exact same invisible force, the electric field, and that's what we're going to get into today. So, what exactly is an electric field really? The textbook definition is a region around a charged particle where another charge feels a force. But I like to think of it like an invisible web. Imagine a charge just sitting there and spinning this web out into space. Any other charge that wanders into that web is going to feel a force, either a push or a pull. That's it. That's the core idea everything else is built on. Okay, so let's get the real handle on this invisible force field. What is it? And why should you care? And it's so important because this is way more than just an exam topic. Seriously, understanding the electric field is like getting a key that unlocks a ton of other areas in physics. We're talking about everything from the capacitors that make your phone work to the unbelievable energy inside a thunderstorm. But here's the thing. To really understand the field, we have to start with the thing that creates it in the first place. We've got to talk about electric charge. It's at its heart. This is surprisingly simple. All matter is made of positive protons and negative electrons. An object only gets charged when that balance is upset. And here is the absolute key takeaway. It's always about the electrons. Electrons are mobile. They can move around. The protons are locked deep inside the atom. So charging is all about gaining or losing those runaway electrons. So if it's all about getting electrons to move, how do we actually do it? Well, it turns out there are three main ways we can give an object a charge. Let's take a look at each one. First up is friction. You already know this one. It's the classic rubbing a balloon on your head trick. When you rub two different things together like a glass rod and a piece of silk, one material literally rips electrons off the other. So the glass rod loses electrons, leaving it with a positive charge, and the silk gains all those extra electrons, making it negative. Simple as that. The second method is even more direct. Charging by contact. It's exactly what it sounds like. If you have an object that's already charged and you just touch it to a neutral one, that charge is going to spread out and share itself between both objects. It's kind of like pouring water from a full cup into an empty one until they both half full. Now for the cleverest method of all, induction. And this one is almost like a magic trick. You take a charged rod and bring it near a neutral sphere. The key word is near. You don't let them touch. The rod's field pushes the similar charges in the sphere away and attracts the opposite charges. Then, while the rod is still there, you give those repelled charges an escape route, like a wire to the ground, and poof, they're gone. Remove the wire, then remove the rod, and presto, the sphere is left with a net charge, and you never even touched it. Okay, so we know how to create charges. But how do they actually behave when they are around each other? That's where we get into the forces and the formulas that really govern how they interact. And this is the big one. This is Coulomb's law. This single beautiful formula is the key to calculating the force between any two charges. It's one you definitely want to have memorized. It tells you exactly how strong that push or pull is going to be. So let's break down what each part means because it's crucial. F is the force. in newtons. Q1 and Q2 are just the amounts of charge, measured in coulombs. R is the distance between them, and watch out for this one. It's a common exam trap. It has to be in meters. And K is just a constant number. You plug in your values and you get the force. And what does that force actually do? Well, it follows these two simple rules you probably already know. Opposites attract, so a positive and a negative charge will pull towards each other, and like charges repel. So two positives or two negatives will always push each other away. Coulomb's law just puts a number on how strong that push or pull is. This brings us right back to the field itself. How do we actually measure its strength? We use a concept called electric field intensity, which we call E. The best way to think about it is this. It's the amount of force that one single positive charge, 1 coulomb, would feel if you placed it at that exact spot. So the formula is just the force divided by the charge. It's simply the force per coulomb. So how do we visualize an invisible force? We use this really clever tool called field lines. Think of them as a map of the field. They always show the direction a positive charge would get pushed. So they always flow away from positive charges and towards negative ones. There's a super important rule. They can never ever cross. And one more thing, the closer together the lines are, the stronger the field is in that area. All right, theory is great, but let's make this practical. How do we actually apply all this to solve the kind of problems you are going to see on your exams? We're going to walk through an actual past question from a WAEC paper. This is going to show you exactly how to put the formulas and the concepts we've just talked about into action. So here's the setup. We've got a positive charge and a negative charge, and there's this point, we'll call it P, sitting somewhere near them. The mission is to figure out the total or the resultant electric field strength right at that specific point P. Okay, we don't just jump in. We make a plan. First, we'll calculate the field created by just the positive charge. Then we'll calculate the field from just the negative charge. Step 3 is absolutely critical. We figure out the direction of each of those fields. And finally, since both fields are hitting point P at the same time, we add them together like vectors to get our final answer. So after we plug the numbers into our formula for both charges, we find something really interesting. The positive charge creates a field that pushes to the right, away from it. But the negative charge also creates a field that points to the right because it's pulling towards it. See that since both fields are pointing in the exact same direction, we just add their strengths together. This gives us a final resultant field of 5.625 times 10 to the power 5 newtons per coulomb, and the direction is to the right. So let's wrap all this up. What are the absolute must-know things to make sure you have this topic on lock? If you remember just one thing from that problem we just solved, please let it be this. The electric field is a vector. That means it has both a size and direction. An answer without a direction is only half correct. And that means you will lose marks. Always, always, always specify the direction. So there you have it. From the basic idea of charge, to how we create it, to the laws that control it, and finally, how to solve a real exam question. You now have the fundamental tools you need to understand this incredible invisible force. The key now is just practice. Keep working through problems, and you'll be more than ready to go in there and ace that exam. For more practice questions and solutions, visit examkp.com.